Okay, so now we have the Euler-Lagrange equations of motion, but to use them, we need to know what the Lagrangian density is. So what we're going to discuss now is let's construct the Lagrangian density for a free scalar field. And so let's discuss the principles that go into this. So the first principle, which is, after all, why we're doing the Lagrangian formulation anyway, is that we want to build in Lorentz invariance. So we would like the Lagrangian density itself to be Lorentz invariant. So L must be Lorentz invariant, okay? So let's just discuss what that would mean. So, we would be allowed to take the field phi and raise it to any power of n. That would be a perfectly good term in the Lagrangian density because phi itself is a scalar field. So phi to the power of n will also be a scalar. If we wanted to take phi to the n and multiply by d mu phi, that would not be an allowed term because d mu phi is a 4 vector and that index is not contracted. So what I could do is I could contract it with a second phi, and that would now be a perfectly good term. What is inside round brackets, there's Lorentz invariant because it's contracted. So I could raise that to the power of m. So that would be an allowed term. But I could have something like, I don't know, maybe phi to the n, then I could have d mu 1, d mu 2, up to d mu k on phi. Then I could choose to have d mu 1 phi, d mu, sorry, let me just, I want to write indices properly contracted, which means that it must appear once up and once down. I could have a d mu 2 phi, and then I could say have d mu 3 all the way up to d mu k acting on phi. The only rule is all of the Lorentz indices must be contracted, and the Lorentz indices are introduced by taking derivatives. Okay, so this already constrains what the Lagrangian density can be in a very, very big way. Good. So it must be Lorentz invariant, and by now you know what that means. We can use the field and derivatives of the field, and any terms that we put into the Lagrangian density must have all 4 vector indices contracted. Next thing that we'd like to discuss is we want to discuss a free scalar field. So how do we put in the fact that the field is free? So free field means what? Okay, that's what we'd like to discuss now. So what does a free field mean? So I'm going to suggest the following. Let's imagine that we found our equation of motion and we find out that phi 1 of x is a solution. So this is just some field configuration. Perhaps the field is non-zero in some region and it's wiggling in some way. And let's imagine we keep searching and we find that phi 2 of x is also a solution. If both phi 1 and phi 2 are a solution, then I claim that when we say the theory is free, what we mean is that phi of x, which is equal to phi 1 of x plus phi 2 of x, this is also a solution. So let's just discuss that a little bit. Why do we claim that? Well, if I've got some solution, phi 1 of x, the field wiggling in some configuration that is a solution, and phi 2 of x is a second solution, then if I add the two, if the field is a non-interacting field theory, then the phi 1 of x configuration shouldn't even know that the phi 2 of x configuration is there. So they should not disturb each other, which means that they both happily continue to be solutions and no problem, the sum of them is still a solution. So how can we say this? So we can say free theories enjoy the superposition principle. Okay, so if you've got one solution and a second solution, the sum of them is also a solution. The sum of any number of solutions will still be a solution. Now, what does that mean if sums of solutions are still solutions? Well, I claim this means the equation of motion is linear in the field phi. Okay, and you can easily check this, but let's do a check together. And let's imagine that our field equation looks like this. We've got d mu phi, so our properly contracted things. There's an m squared phi, then I'll add in some coupling, and I'll have a phi cubed is equal to 0. Now, this is not linear. It's not linear in phi. Not linear. And it's not linear because of the phi cubed term, okay? So let's just check if this theory obeys the superposition principle or not, okay? Good. So imagine we've got a first solution. So we have found a phi 1 that obeys this equation. And then we've got a second solution. So we found a phi 2 that obeys this equation. And now what we want to check, does phi 1 plus phi 2 obey the equation? Check. Is phi equal to phi 1 plus phi 2 a solution? Well, let's check it. Let's plug in phi 1 plus phi 2. So we've got d mu. Instead of phi, we write phi 1 plus phi 2. Then we've got plus m squared. Instead of phi, we write phi 1 plus phi 2. And then we've got plus g. And instead of phi, we write phi 1 plus phi 2 cubed is equal to 0. And that's what we want to check. Is it 0? We don't know if it's 0 or not. So let's simplify this. Well, we've got d mu phi 1 plus d mu phi 2 plus m squared phi 1 plus m squared phi 2. And now from this last term, we've got g phi 1 cubed plus 3g phi 1 squared phi 2 plus 3g phi 1 phi 2 squared plus g phi 2 cubed. And now notice, if I take this term, add it to that term, add it to that term, that vanishes because phi obeys the equation of motion. So those terms I can drop. And notice this term plus that term plus that term also vanishes by the equation of motion for phi 2. So I can drop those terms. So what I land up getting is 3g phi 1 squared phi 2 plus phi 1 phi 2 squared. And this is not 0 because phi 1 and phi 2 are not 0. So phi 1 plus phi 2 is not a solution. And what spoiled it is the term with the g, which means the term which is not linear. If I didn't have that term with the g there, phi 1 plus phi 2 would have been a solution. So to summarize the argument, and you can check more examples if you like, okay? But to summarize the argument, we're saying that if you have a free field theory, you must have the superposition principle. So I can add solutions and the sum is still a solution. And that means the equation of motion must be linear. Okay? So we want an equation of motion that is linear. Now look at the Euler-Lagrange equations, okay? On the one side, we've got dl d phi. So if we want to get something linear after we differentiate it, what does it mean? Well, if we differentiate something with respect to phi, and the answer is proportional to phi, it means that whatever sits there must be proportional to phi squared, okay? And exactly the same argument for the other side of the Euler-Lagrange equation. If we differentiate with respect to d mu phi and we get something linear in phi or linear in d mu phi, that's also fine. It means that we had to have something quadratic to start off with. It's only quadratic things that when differentiated give you something linear, okay? I think that's obvious. D by dx of x squared is just 2x. It's quadratic things that when you differentiate, you get something linear. So the free field means we want the superposition principle. That means the equation of motion must be linear. And that means the Lagrangian density must be quadratic in phi. So we must, all of the terms inside the Lagrangian density must be quadratic in phi. Very good. We'll continue in a moment.